And now we're going to give an even bigger, even warmer round of applause for Alex and Moritz, who's going to talk about getting rid of nuclear weapons. Give it up, louder.
Thank you.
Thank you.
Thanks. Thanks everyone for joining us. I'm Alex. And this is Moritz, and as he just said, this is a talk about nuclear weapons. Both Moritz and I, and also our colleagues back in Princeton, spent most of our time trying to get rid of them. But so far, we haven't made much progress, especially lately. And 2017 was a particularly difficult years. But in this business, you're in for the long haul. You have to be persistent. And you want to be ready when there are new opportunities for confidence-building, arms control, and nuclear disarmament initiatives. Now, for this talk, what's relevant is that any new initiative toward further reductions in the nuclear arsenals will have to rely on robust verification mechanisms. And as you will hopefully see today, verification will have to rely on trusted radiation measurements. After 25 years of R&D in this area, no winning technology has emerged. And ultimately, it boils down to a lack of trust in the electronics that is being used for these applications. So Moritz and I thought, well, perhaps vintage computing platforms may offer a new answer to provide an answer to this challenge. And so we brought some gear, and hopefully we'll demo it in a couple of minutes. But before I get to this, let me just briefly summarize where we are today with regard to nuclear weapons. There still remain about 15,000 nuclear weapons today. More than 90% of them are owned by the US and Russia. And then you see 7 other nuclear weapon states in the world. Unfortunately, these numbers actually haven't come down by much over the last 15 or 20 years or so. And by any meaningful standard, it's a gigantic number. New this year was the North Korean latest test in September, where North Korea, for the very first time, conducted a test, a large nuclear weapons test, 250,000 tons of TNT equivalent. And we believe this was a two-stage thermonuclear weapon, and it's significant in many ways because North Korea only tested 5 or 6 nuclear weapons before that, and it certainly now has a credible nuclear capability, and also the means to deliver this weapon. We call it the peanut here. You can see this typical shape for a two-stage weapon with a primary and a secondary. Now, in the interest of time, I will not walk you through the global consequences of a nuclear war, even a limited one, and they are pretty bad, as you might imagine. And personally, I believe even a single nuclear explosion in a major city would in many ways be the end of the world as we kind of know it, and not in a good way. Obviously, with a 200 kiloton explosion, you could wipe out an entire city in an instant. Now, lately there has been quite some loose talk about using nuclear weapons again. We haven't seen this in 20, 30 years or so. There is talk in Washington about a preventive nuclear war against North Korea, and that is disturbing. And I'm afraid there will be more of this in 2018. And this tweet here kind of summarizes the situation quite well. You can't lose the 2020 election if there is no 2020. However, there has also been some positive developments this year. Early in the summer, 122 nations at the UN in New York negotiated a nuclear weapons ban treaty, which places nuclear weapons for the very first time in the same category as biological weapons, chemical weapons, cluster munitions, and landmines. For obvious reasons, the weapon states did not participate in these negotiations, but the idea is they will join along the way. Since we're here in Germany, and I'm a citizen of Germany, just as Moritz, it's worth mentioning that Germany too voted against the resolution in 2016 to start negotiations on such a treaty. I don't want to be dwell on this too much. I personally believe this is a mistake. It would be the right thing to do for Germany to join this treaty, and it wouldn't be particularly difficult for Germany to do so. And just to close on this, and just earlier this month, and this is it is a big deal. ICAN, the International Campaign to Abolish Nuclear Weapons, received the Nobel Peace Prize just for this reason, to facilitate the negotiations of this treaty. And you can see some of the key folks who've been involved and kind of made this treaty possible. So this is really one of the highlights of this year. Now, but coming back to the purpose or the topic of this talk. So what is to be verified? I already mentioned it's going to be critical to have verification mechanism in place. It's particularly important also for the ban treaty, where you try to verify the number 0. And the United States, for example, has actually made the point that the ban treaty cannot be verified, and for this reason it should be boycotted. Which is nonsense, of course, but you get the idea. People do take the verification question very seriously. Now, to kind of highlight or illustrate what it involves, we have this cartoon here of a fictional nuclear weapon state. Has a bunch of nuclear facilities. Some of them are civilian, and you may find them in other countries too, enrichment plants, reactors, and so on. Some of them are military, and they're highlighted here in blue. And the main difference between a weapon state and a non-weapon state is that the weapon state has nuclear weapons, and they move around the weapons complex, right? So what we're trying to do is confirm certain constraints on these weapons, limits on the number, and the number again could be 0. And there are important challenges that you have to resolve when you try to verify such a treaty, and I highlighted them here on this cartoon. We could give talks about any one of them. But today we want to talk about one specific one that's typically considered one of maybe the most difficult one to address, which is confirming the authenticity of a nuclear weapon. So in a sense, the scenario is, your counterpart, the Russians, the Americans, whoever shows up and says, look, we have 100 nuclear weapons here, we want to dismantle them, and we want to get credit for this, right? We want to kind of have these reductions on the books, and how do you make sure that whatever they present to you is actually a nuclear weapon or a bunch of nuclear weapons? That's the challenge, and that's what we're trying to solve today with vintage verification. So how do you do that? So the first thing we need to know, and it's really the only thing we need to know, is that nuclear weapons, any nuclear weapon contains fissile material, nuclear explosive material. And I put the numbers here on the screen. Typically 3 to 4 kilograms of plutonium, for example, is enough, or you could expect this in a nuclear weapon. And that's about the amount of plutonium you would have in a nuclear warhead. I was told this is aluminum. And again, anything else really doesn't matter too much for our purposes. The key is it's plutonium or highly enriched uranium. Both of them are radioactive, and we can use this to detect them from a distance. Now, the issue is, so they have unique radiation signatures, but they are highly sensitive and they cannot be revealed to inspectors. The only exception is really the one you see here on the screen. This is a bunch of US scientists, actually some of our colleagues in Princeton involved, who went to the Black Sea in 1989 and made a measurement on a Soviet, at the time, nuclear weapon, and published the spectrum in Science magazine. And here you go. It turns out you can actually learn quite a lot from this spectrum. So in the aftermath of this exercise, weapon states concluded, well, we cannot really do this anymore. This was kind of a bad call to go this way. So then a couple of new concepts were developed, and we've implemented one of them in this box over there. The first one is, okay, I can't possibly show you the spectrum that you just saw, so we have to kind of do it somewhat differently. The first idea they came up with is the attribute approach. You say, okay, you cannot look at this weapon or at this component, it's in a container, but we can agree on certain attributes. So you sit down with the Russians and say, well, we have plutonium, you have plutonium. That's an attribute, and both sides would agree, okay, yes, you can confirm that there's plutonium in this container. That's one attribute. Maybe there's a certain minimum mass. It has to be more than 1 kilogram. And we can do this also with radiation detection measurements, more than 1 kilogram. Certain isotopics. Even the geometry or the size or the mass you can detect with radiation detection equipment. So you make a list of attributes. One approach, we don't really like it particularly much because it's obvious how you would defeat it. Because if the threshold is set at 1 kilo, I just need to present 1.1 kilos. It will always pass the test. That's one way to do it. And the second one is the one we are using here for this exercise or this experiment, is the so-called template approach. You do acquire one radiation spectrum from what we call a golden warhead, reference item. You store it perhaps in some way. And then when down the road the other side shows up with a second item, you compare the two signatures against each other. And if they match, you say, okay, I accepted the first one, I will also accept the second one. So that's the template approach, and we'll do this later in a moment. So in both cases, you do acquire sensitive information, right? I mean, the radiation detector will see everything. So what you need is a third idea, which is called an information barrier, which is really just a piece of electronic equipment that will do the data analysis and then only display kind of a red light, green light, pass, fail, go, no-go result. Okay, it will not display the actual spectrum. And that's the main idea of an information barrier. And coming back to, why is this, such a difficult job? The problem is, how can both sides, the inspector and the host team, trust the technology at the same time? Okay, so the host is worried that this machine will accidentally release the secrets, right, through some side channel or so. And the inspector is worried that the machine is actually not doing anything meaningful and will just display, the result that the host wants to see, right? So this is actually something that a Russian nuclear weapons expert said when he or she was invited to a visit at a US weapons lab. You have some machine that, does something. I have no way of knowing that this is actually a genuine measurement. So that's essentially where we are today with, the state of the technology. Let me just, wrap up here quickly before we move into the demo part. Why are they so hard? I already summarized some of this. So first is, and it's very unusual for an experimental physicist or so, that you actually don't know what you're looking at, except for the fact that, it's plutonium or so. So you cannot reveal, or you do not want to reveal, about what's actually in the box. Some information may be shared in advance, but you certainly don't want to learn anything else during the inspection. The second part is, we're talking US, Russia, China, and the rest of them. Your adversary has de facto infinite resources, okay? And the adversary may be, quite motivated to actually defeat or deceive your system. And just as one data point, the US is currently or refurbishing one US nuclear weapon, the B-61 Mod 12. Refurbishing that weapon costs more than $30 million. One weapon, $30 million, which is more than the weight of gold of that bomb. So a government is willing to pay $30 million to refurbish one weapon. You might imagine how much resources it may throw at, a system. They might actually, pass fake nuclear weapons as genuine. And then finally, and that's, for this community in particular, the most difficult one, or, ironic one. The host has last ownership of the inspection system before the measurement. So they walk away and, you don't know what they're doing with it. And the inspector never again has access to the system after the measurement is complete, because there may be some form of, classified information left in the system. So that's essentially why these inspections are so hard, and which is why we thought, can we offer an alternative with vintage technologies? Now it's time for Moritz to proceed. Here you go.
So, as we heard, it's hard, and if you look around who build such systems, there actually have been less than 10 built in the world, which is very few for 25 years of development. I'm going to introduce 3, and then we're going to start up the computer that we have set up there. One is called Trusted Radiation Identification System, or short TRIS, built in the end of the last millennium by the SANDIA National Laboratories. And this is how it looks like. It's based on the template approach, so it measures a sample and then compares this to an item you want to inspect. For this, it uses a simple sodium iodide detector. It's a radiation detector that detects gamma rays. It's very rough in the spectrum that it generates, but it's good enough for the purpose. It runs from a 12-volt battery, and it has something that's called a trusted processor in this metal enclosure. There's actually 2 processors and some more hardware that's installed in there. It doesn't have a green light, but it has a display and a keypad. So you control it by this keypad, and you display the result on the display. And these small little weird-looking things on the left of the picture, they're so-called I buttons, and one of them is actually used to store the template. They're basically just, small memory things you can plug into this trusted processor. So what we like about the TRIS system is it's very simple in its detector setup. It's passive, and it uses this low-resolution measurement, so you don't generate too much information that might then be given to someone you don't want to give. And it also uses a strong temper indicating enclosure. So SANDIA National Laboratories actually are pretty good in building these things for a variety of purposes. So this is this metal box. Inside of this, it's actually divided in 2 sides by a big metal plate. One side is called the red side, the other side is called the black side. And they only communicate through 3 small holes by optical means. So they're actually completely electrically separated. The red side handles the classified data, and the black side deals with the display and the keypad you saw. And they also added special temper boards on the sides. You see if someone drilled a hole into this, and make eddy current measurements before and after the measurement to see if someone has dealt with this metal enclosure. And the last thing we like, probably not the last, but the last on this slide, is it's actually pretty fast. So you can measure a template or an inspection in 30 to 60 seconds. And then you take the spectrum, condense it down to 60 numbers, and only these 60 numbers are used to compare it to another item by a simple statistical test. There are also some things that we don't like. So we don't like that it actually uses very complex hardware. Even if this is only in a 586, an AMD K5 processor inside on a PC 104 form factor board, it still has 4 million transistors that you would need to verify to make sure it actually does what it's supposed to do. It also uses an FPGA for the data analysis, and there's actually 2 of these processor boards inside, one on the red side, one on the black side. Also, we don't really like that it's a system built only by a nuclear weapons state in the United States, and its main focus was to ensure that no information is leaked. But they actually also said that this was their main focus, so they had a hard time kind of proving to the site that wants to inspect that the system actually not just only shows a green light or a good sign on the display when it's asked to. There's a second system that's more recent, built actually by a nuclear weapon state, the United Kingdom, and by a non-nuclear weapon state, Norway. They came together in the UK-NORWAY initiative for about 10 years, and they did 2 things. One was they simulated disarmament of nuclear weapon as a kind of live action role play. So they actually walked around with warheads and measurement devices, not warheads, with fake warheads and measurement devices, and so tried to figure out why this is hard. But they also built an information barrier. And this is how it looks like. This is their third iteration. They had 2 they built before, one by UK and one by Norway. And their goal, they had many goals to build this. So they wanted to have a simple device, as simple as possible. They wanted to use off-the-shelf hardware. They wanted to have it modular. So you see it's divided not only by geometry, but also by color into a digital board, an analog board, a low-voltage board, and a high-voltage board. They want also it to operate from battery, so this operates from battery, so it's independent of a power supply. And they wanted it to be very robust for use, and they wanted it to be very clear while you're using it. So they came up with these 3 buttons, and then the middle circles are green LEDs, and the other ones are red LEDs, so there's actually green lights. But they set out to use the attribute approach. So they didn't do the template approach, but they tried to use the attribute approach. And the attributes they picked for this device are the presence of plutonium, a material that you can use in a nuclear weapon, and the ratio between 2 specific isotopes of plutonium, one plutonium-239 and one plutonium-240, sorry. And if this ratio was above a certain threshold, they would show a green light. What we like about this is the clear operational procedure. They had this very simple user interface. You think this is not that important, but if you have a nuclear warhead in the room, you want to make sure that everyone knows what's happening, and there should be no confusion about anything, basically. They also had comprehensive documentation. You can download schematics, bill of materials, and the software that ran on the machine on their website. It took them quite a couple of years, but then it's published now, and we actually learned a lot from this. And last but not least, the most important, this is actually a joint design effort between a nuclear weapon state and a state that does not have access to nuclear weapons. And they were aware of this and analyzed also what problems they had doing this. Same here, what we don't like that much. The system is based on the attribute approach, which in general is harder because you not only have to make sure that 2 things are equal, but you actually have to identify things from everything else. And so they use a high-purity germanium detector, similarly gamma detector, but it gives you a finer spectrum, which they need, but it also requires to be cooled by nitrogen, liquid nitrogen, to be very cold, and it's not easy to do in the field. They also need a very complex algorithm in the box to say, okay, there's plutonium present or there's no plutonium present. And they have the same problem as before. They, of course, there is no real open chip, but they use the closed chip for the data analysis. They limited themselves also to a simple chip, the ATmega 2560, an 8-bit microcontroller for data analysis. When we looked at the schematics, we also found this AT-tiny microcontroller on the so-called analog board, and we were first surprised what this was, but they said they use it for timing issues, but just in a place where you wouldn't expect any digital analysis. Though this shows, this was for us the first example to say, okay, there might be something going on. Why is there a microcontroller where there shouldn't be? And they both have flash that probably could store images, so that might be a problem. The third example we call information barrier experimental, or IBX, something we built 2 years ago. We mostly built it because it looks good, and also because we wanted something to learn, kind of a prototype to actually see what problems could we have, and as a mean to teach people to how you would use this and how you would build this. It's also a template approach. It can store up to 3 templates and then measure an item and say, it's one of these 3 templates. And it also uses a sodium iodide crystal and scintillator as the TRIS system. This is how it looks like from the inside. We try to make it very transparent and also cheap. It's cheap in quotation marks. It's less than $1,000. On the left side, there's a single board computer. On the right side, there's a custom-made board. On the right picture, you see when it measures something. And we also, in a sense, ran into the same problem. We use a complex chip. So we use this board, it's called the Red Pitaya, which is nice because it has this fast analog input we use for data acquisition. But you can only do this if you have an FPGA, basically, because the 14-bit 125 million samples per second need to be processed fast, and if you have a proper processor. And we run a full Linux stack for now, because it was just the simplest thing to do. So then we took a step back, as Alex said, and we said, okay, what else can we do? And we came up with the idea, okay, let's try if we can actually do the same with hardware that is old, and that's called vintage verification. That's the name we came up for it. Why would you do that? You take the best of all worlds, and you try to build a trust through simplicity, and probably also through obsolescence. And we use a simple detector system, again, sodium iodide. It's widely available. It gives you the low-resolution spectrum. And then we use vintage computing platforms. We use an Apple II in this case, which it's relatively old. It has been reverse engineered, even if the specs haven't been published. Not all of them, but it has been reverse engineered quite good. So it's quasi-open source, that's what I called it. And it's unlikely if someone hit a backdoor or a hidden switch in this system 40 years ago for the case that it might be used for warhead verification today. So we think this is not very likely. And another thing why we want to use this is you would like to use the BYOIB, bring your own information bearer approach, where the host country and the inspecting country would go together and shop for hardware, basically either on eBay or go somewhere and pick a device and use this. And as the processor inside of the Apple II, there's the 6502, something we also like very much. It still has fewer transistors than there are nuclear weapons in the world. We hope to change this for the nuclear weapons. It has only 3,510 transistors, runs usually at 1 megahertz, has 56 instructions. But there's an abundant number of these devices built. So the numbers vary depending who you ask, but people say there have been billions of these chips actually made. And they have been made from 1975, and they are made more or less until today. And these are 5 chips that we actually had to play with. And some of them are also in these arcade machines in Alex's living room, and you see his kids testing our verification processors, if they work good or bad. And they're also in the Apple II. It's the 40th anniversary this year also of the Apple II, so the computer is older than I am, and that made it a fun project to develop radiation measurement cards for this. Why would we use that? Why would you use an Apple? If you look at Apple today, you just think, what's the benefit of doing something with an Apple? But when this was developed, it was actually, I think, probably the last time that hackability, or the ability to extend your system, won in the company policy over seamless end-to-end user experience. So when they developed this device, their first home computer that actually came in an enclosure, the two Steves, Steve Jobs and Steve Wozniak, had a fight about how many extension slots this device should have. Wozniak said it should have 8 slots so people could do whatever they like. They could build cards, they could build things, and they could probably verify nuclear warheads at some point. Jobs said there should only be 2, one for a printer and one for a modem, and that's enough. People won't do more with that. So we are happy that Wozniak won. And you can see this on the main board. This is a main board of an Apple IIe, which is kind of a slightly more advanced version of the Apple II. In this case, forgotten the year. I think it's from '82. Yes, this is a board from '82. This is the board that's actually on display here on the table, and it has these 8 expansion slots. And it also has some standard computer hardware. It has the 6502 processor, and it has a ROM and RAM, so we can start using it without building our own computer. In theory, of course, you could just take the 6502 and then take some RAM and some ROM and plug this together and make the same measurement, but that would be a step further than just developing cards for the Apple II. And with that, I think it's time to actually turn it on for the first time. And I hope it works. We'll see. Can you switch the video?
I don't know if the camera can see this yet, but anyway, turn it on.
The floppy disk is not inserted.
Okay. Start with this.
All right.
The floppy disk was missing. Yeah? Okay, here we go. So first we need to ramp the high voltage. The detector typically needs on the order of 1,000 volts. And Moritz is going to walk you through the details of the boards. So now the high voltage is up, and we can acquire the first template. So we're fortunate, friends from Bochum brought us a small calibration source that we can set in front of the detector. So we can actually get a signal. So we acquire the template. And here we go.
Of course, in the actual measurement setting, you wouldn't see this spectrum. This is the thing you actually want to have classified, but we thought it's more useful to show to people here that this device is actually acquiring data.
So this is a cobalt-60 source for those of you, who are not in this business. And people like cobalt-60. I mean, if you like radioactive sources, I guess, because it has these two peaks that you can see, and it helps you really understand, the sensitivity or the resolution of your detector. Anyway, this is going to count until to the 17th count, I guess.
Yeah. So we go back to the main screen. If we let this run in the background, we come back to this after a while. Probably Alex actually has to push a button on the computer to acquire.
There's one issue. The detector has to warm up a little bit. So ideally, would have to wait 5 minutes or so to stabilize the high voltage. So we'll see how we'll be doing on the verification or the inspection in a few minutes. Okay.
So what just happened? Just a very quick physics 101. We had gamma rays coming from this source. That's one type of radiation. And the gamma rays hit a scintillation crystal. That's something that's this shiny blue thing. So it's basically a material that absorbs this gamma ray from the radiation source. And it emits other photons, but photons that are more like standard light. And it emits about 38,000 photons for a single gamma ray with the energy of 1 MeV. And these peaks at 1.2 MeV and I always forget the exact number, but a little bit above 1 MeV. So all these photons get emitted in the crystal, and then they hit this photocathode, which sits at the end of the crystal, and they produce electrons. And these electrons then get amplified by something called the photomultiplier tube, which is a tube where the electrons get accelerated from the cathode towards the anode. And on the way, they hit these curved surfaces, which are called dinodes. And whenever they hit one of these, they produce more electrons. And when they end up at the anode, one electron from the start is 10 million electrons on the anode. So it's a very, very efficient amplifier for small signals. And then the anode is charged with a lot of electrons. But as we saw in the demo, it needs high voltage. And so we designed a high voltage board first. We cheated a little bit on this here. We use this CAN or CAN module, which produces the high voltage for us. We give this 12 volts and a set voltage between 0 and 2.6 volts. And from this, it makes proportional 1 kilovolt up to 1.6 kilovolts, or 1,600 volts. And we didn't want to play with this voltages starting to do electronics. So we use this module, but we want to replace this. And we build a very simple digital to analog converter, which you can see in the middle, based on an R2R network. And this gives us this V set, and it raises this over time to protect the scintillator. And then, of course, we had to build a data acquisition board, a board that takes the electrons that sit on the anode, feed this into this BNC connector on the left, process it, I will come to that in a second, and then give it to an analog to digital converter. We use a 12-bit flash ADC that has, luckily, an 8-bit bus interface, because the 6502 only has 8-bit data interface. And we have some control logic, and we actually also have some LEDs, red, yellow, green, and some blue ones. But we decided for this demo that we would not use them. So in the analog part of the board on the left, first you get the signal. It's pre-amplified. It doesn't mean it's amplified, but it's something that sits in front of the amplifier. And it takes these charges and converts them into a voltage pulse by a charge-sensitive op-amp circuit. And you see it's a fast rising pulse, but it decays slowly over time. So the next thing we do is differentiate the signal by a differentiating op-amp stage. And so the decay is shorter, but then it gets inverted. So we use an inverting stage. Oops. We use an inverting stage to flip it back up, and also use a trim pot to adjust the gain, because depending on the build, actually, and the resistors you used, you always have to adjust the signal so it actually fits in the ADC voltage range. Then we do some pulse shaping. It's to be noticed here that actually the scope shot, this is shots from our oscilloscope, it takes a much wider time range. And you see that the rise time of the pulse now is slower. And we did this to detect this pulse easier. Instead of fast rising, we now have a relatively slow rising pulse. And then we feed this in the biggest and most confusing stage, which is the peak detect and hold area. And it also does the ADC timing. And I will go through the oscilloscope shot on this in detail. The yellow line is the line of the output of number 1 on the previous slide of the charge collecting op-amp stage. The blue line, this is what the peak detect and hold circuit actually gives to the ADC. And you see this is very nice because it rises up to the peak and then it holds the voltage of the peak and gives the ADC time to convert this. And I forgot to mention, of course, that the height of the peak is actually proportional to the energy of the gamma ray that we detected earlier. So we hold this voltage for a while. And then we use the purple, which is a digital signal, produced by a comparator. We say, okay, when it raises above a certain level, then we should probably start this conversion. And then we wait a little while until the signal is flat, and then we emit the green digital signal to the ADC, and say, okay, now you can start the conversion. And then if you look far to the right of the picture, you see that the signal goes down again. And this is actually the time when the ADC has done the conversion. It takes about 10 to 15 microseconds. And the Apple II has read the 2 words from the ADC and stored them in channel in memory, and also increased the total counter that counts the total number of events. So it did some logic, and the whole process only takes about 60 microseconds. And if you remember, it's a 1 megahertz CPU, and it leaves like 40 microseconds for the processing. It means it's actually 40 clock cycles. And I guess if people would look at this, they might even come up with a faster assembler code. But that's a reasonable time, and we were surprised in the end how fast we could actually sample signals. Before we go back to another demo, just a few lessons I learned. I don't know how many people in this room have built hardware, probably a few. I'm a physicist. I did simulations most of my time before I started doing this, so I didn't build hardware. And then I set out to build hardware for a machine that is older than me. So how would you do that? You actually start reading actual books. So there's some manuals online, but the best thing I did for this project was to go on a bookstore and buy old books. They're actually cheap, and they describe a lot of things that happen in this Apple II, and also general things about electronics. And then you have to design some things, and you have to try, and you have to repeat. And the best thing I figured out was when I build a breadboard that doesn't work. This is the breadboard where I set up the ADC card. When it doesn't work, the best is just take a new one and start again. And then, probably it works then, and you have better ideas, or you're more awake because it's the next day. And last, for this, it's important, and it keeps you motivated to choose a real-world problem. And this could be anything from, changing the heat or turning on and off the light in your room, watering plants, having an Apollo guidance system fly to the moon, or getting rid of nuclear weapons. And one of the benefits of working on getting rid of nuclear weapons, it's not a benefit. Actually, it's a disadvantage. The last year was bad, and there were many sleepless nights worrying about what Trump and Kim Jong-un might do. So when I couldn't sleep, I could actually at least work on something that might be useful. And if you want to try this for yourself, the software for the Apple II is online. There's also a repository for the hardware. And if you don't happen to have an Apple II, which is probably likely, there's also a repository which has an emulator for the Apple II, where I added special emulation for the cards we built. So you can actually test out the software, loading the disk that we did just on your normal Linux computer. And now we go back to another demo.
Can we switch back to the, here we go. Okay, so here's our template. So we could either now inspect the valid item and not touch anything, or if we had a second item, a second source, we could, kind of try and inspect a fake weapon. Let me see. Let's do an inspection here. I haven't touched the source. If you watched me in the meantime, I actually acquired a second template, kind of, doing it again, hoping that the high voltage did stabilize in the meantime. So we're now inspecting. We haven't changed the warhead, so to speak. So we hope it'll pass, but I can't promise. Do we have a second radioactive source in the audience? Let me see. Here we go. Yes. One of our friends was kind enough to bring one along. I can tell you, international air travel with radioactive sources, not recommended. So we tried to find them in Germany. They are, of course, completely harmless. So let's just wait until this one finishes. I can tell you when you start calling your friends, you know, look, I need a radioactive source. I want to take it to Leipzig to the Congress. People tell you, look, you know, I'm sorry, I can't help you with that. But some do. Yeah, so thanks for that. So here we go. Again, the code actually, most of the software does the display, which wouldn't be in the final version of the software, so to speak. Right now, how many bytes do we have? 2,000?
It's 2.5 kilobytes, but most of this is the display strings you see and the code that actually displays stuff.
Okay.
And now comes the...
So let me put the check. Okay. Pass. Chi-square statistic hex 12, which we'll see that's actually pretty good. So now I have the second source. Let me just throw it, you know, somewhere on the table. And let's run another inspection. I hit the 3. And, well, you can actually, I guess, if you watch the previous one carefully, you can already see there's a new peak, you know, showing up on the left side. So, you know, it really should fail by that, by now. If you have anything to add in the meantime while we're waiting?
I think we can, you know, do the announcement basically. If you after this talk there will be other talks, so we have to leave the stage quickly. But if you want to have a closer look at the device, we're going over to the CCCL, and we will be at the Forum Informatikerinnen für den Frieden area, which is on the first level, I think. And we just set it up there. So if you want to have a closer look at this, you're invited to come over and see. We might not bring the sources just for security, you know, just bring the device and...
Just one thing, you know, in case I forget it at the very end. I mean, you know, I'll wrap up in a moment. But the one thing I think that we did definitely show with this, you know, is the 1 megahertz processor is actually, you know, fast enough to do this right. I mean, we get about 2,000 counts per second. Which is actually not a bad number for this type of application, and that's you know, that's 1 megahertz chip is just enough. So here we go. It's complete. I hit the check, and it failed. And if you see the hex score here is pretty significant. More is the machine language coding here. Okay, can we switch back to the main screen? Okay, so I could very briefly in just 2 or 3 slides explain what the code is actually doing, which is actually the beauty of the template approach, and it's inspired by TRIS. So here's a real-world spectrum, you know, looking a little fancier than the ones you just saw, but basically the same thing. Imagine yellow is a valid item and orange is the invalid item. Here we have, and you see there's one area where they're kind of different. But otherwise they look, you know, pretty similar. The first thing we do is we divide it up into a number of bins, small number. We pick 12, but you know, there's nothing special about 12, small number. And then we take the average count in these bins. So it's a very, very low resolution spectrum, or histogram, if you will, of this radiation spectrum. And then we just compare yellow versus orange and take the chi-square statistic for, you know, 12 or 11 degrees of freedom. And the nice thing is that, you know, you see the equation up there. You know, you need to subtract 2 numbers, multiply the difference, and divide by, you know, another number, and you do this 12 times. Even in machine language, you know, it's pretty straightforward and easy to implement. When you do this for this particular example, you get for a valid item a chi-square of around 10, and you see, you know, distribution. You then you know, define, okay, what is green, what is red, pass and fail. And if you take the orange one, which, you know, wasn't quite, it wasn't very different, but in terms of the chi-square, it, you know, it looks drastically different. And you're done. You have a pass-fail algorithm. Pretty simple. So, wrapping up, you know, where do we go from here? You know, can we actually turn this into a viable device for trusted measurements? You know, maybe with the help of this community here. So there's a bunch of things, obviously, that we would have to do. You know, revising the software and the hardware, clean up the code. There's a few things that we actually haven't done yet. Subtract the background. You know, correct for detector drift and so on. Replace the high voltage module. You know, pretty straightforward. We also probably want to package the board or the whole equipment in some type of serious enclosure. So that's robust against tempest attacks and so on. But the one thing that is probably the most important one, everything kind of hinges on that particular one for this particular idea is, can we actually prove that the processor in this Apple II, the 6502, is authentic, it's genuine. This one was pulled from the Tempest machine that you saw earlier on the picture. But can we prove that the processor is the real deal? Because if we can't, then we haven't really, won a lot. So the Apple II board, Wozniak's masterpiece, Moritz showed it already. People have done amazing things with the 6502. The visual6502.org have done these very high-resolution optical images of the die, built a transistor-level simulation of the 6502. It's kind of destructive analysis. What we hope we'll be able to do is, or we ask, can we do this in a non-destructive way? Not the simulation, but the imaging of the chip, so that you can actually confirm the architecture, the original architecture of the chip, because we want to use the chip afterwards, obviously. And we hope we can take advantage of the fact that the chip is made with 8-micron technology. It's huge compared to what we use today. It only has 3,500 transistor, and it's very, very well understood. We think there may be several options to do this. I mentioned the high-resolution X-ray microscopy. Ideally, if we could age date the chip, or the package of the chip using some forensic techniques, that would be fantastic proof of provenance of the chip, or perhaps even some logic testing to confirm the original architecture of the chip. Again, we hope we can leverage in some way the deep understanding of the 6502, at the transistor level for this purpose. I think that's all we have. We posted everything on vintageverification.org, the slides, the code, the hardware designs, and as Moritz mentioned, will be outside if you're interested, and demo the hardware. And with that, I guess we're happy to take questions.
Okay, so we have some time for questions. So please come closer to the microphones, raise your hand, and we'll take the first one from the mic number 5.
Hi, great talk. One question. You said that you need to verify the chip that's authentic. Can you not do this afterwards, after you use the chip for the measurement? And do the destructive analysis afterwards?
It's a good question. I think my answer would be probably not, and because the damage would be already done in a way. That's also why cut and choose approaches, where you put 10 on the table and just pick one and inspect the others at home, may not be good enough for this type of application. The other side would say, look, the risk is after the fact you learned already our weapon design, and it's kind of too late. So ideally, we really want to do it before we actually use it for the inspection.
Okay, thank you.
Now, number 1, please.
Oh, there was 3.
Hi, thank you for the talk. My question was about the, you had stated that you were concerned about side channel potentially leaking some information about like the spectra or what you were processing over, and I was kind of wondering how you would address that with a 6502 CPU.
That's probably the question we feared from the audience. We basically haven't thought of this in detail, and of course you would have many side channels in the 6502. But at least that's my layman assumption, is that if you can run it from a battery in an enclosure that is RF resistant enough, that the system would be simple enough that people would know all the flaws and then protect against all the ways you could actually get into the system. Whereas if you would take a modern chip, even if it's a simple chip, that's many of the talks here, you always find out afterwards that actually there's a way to listen into what the chip is doing. with the 6502, people have tried to do this for 40 years. We think this makes it secure than, not a full proof, of course, but it makes it secure than a new chip.
Let's go to microphone number 3.
Great talk with great toys. I mean, what you did is you made gamma spectroscopy available with much lower, cheaper, simpler equipment than other people. Do you also have an idea where to get sodium iodide scintillator material so that you could do different spectroscopy applications at home?
You can actually order sodium iodide crystals on eBay or online, and they're freely available to everyone who wants them, and they're not even expensive. And you can get the whole set of crystal with the photomultiplier, which needs to be light, has to be blocked out. So this is why it's silver shiny, so all the light that is inside stays inside and no light from outside hits the photocathode. You can buy these things actually in old on eBay for you know, a couple of you know, 10, 20, 100, depending on where you get this from, dollars or euros.
Does that also apply to rat poisoned cesium iodide? Thallium doped.
I guess probably not. I haven't checked. I wouldn't know. But this detector.
And this is why we like these detectors. Yeah. I mean, there's nothing more abundant than this type of detector. You can find them on eBay, and they're really affordable.
Thank you.
More questions? Step up to the microphones. And microphone 3.
Thank you. Have you gotten in touch with Woz at all, or have you wanted to, or needed to?
You mean with Steve Wozniak?
Yeah.
Not yet. Maybe after this talk. I mean, literally, if you knew when we finished this project, you'd be, kind of just a few hours ago, so to speak. But now we have something that actually works, and I'm not actually sure what we would ask him, but I hope he'll like it.
Cool.
Thanks.
Okay. More questions? We still have a little bit of time. Maybe for one more question.
We can run more inspections if you want, huh?
Okay, good. Someone's coming up. Microphone 1.
So thank you very much for the talk. Maybe a very naive question. But what is secret on the spectrum? What can you learn from a spectrum? It's not the receipt of Coca-Cola, I guess.
Yeah, I have to go back all the way to the beginning. But, I mean, you could make the argument, and I think it's a valid one. I mean, it's something, especially from a non-weapon state, you should ask. I mean, what's the big deal about your secret? It would be so much easier, and that's a true statement, an obvious statement. If you revealed the secret, then you wouldn't have to protect it. And it's always worth asking, what exactly do we have to protect? Kind of a middle ground here is we believe that these 12 numbers. They may be just on the edge, where a weapon state might say, look, you know what, these 12 numbers for the template for this particular weapon type, we might as well put them out there, and we don't have to protect the template. That would be a big deal. But in general, the idea or the concern would be that you can actually learn, more or less the design of that particular weapon. And they are weapons, so people try to defend against them. Your adversary might learn exactly how you designed your weapon and may actually come up with an idea to defeat it. And again, I'm not subscribing to this viewpoint, but that's obviously something that people would bring up. And weapon states have invested billions of dollars into this technology, and because they think they need it, and they will protect the secret. But the question about revealing the secret is a very important one. And we shouldn't just take it at face value. Yes, we have to protect every secret that you say is a secret. And I think the argument, if you actually give us, if you're being more transparent about certain things, the verification part gets so much easier and maybe less intrusive, and it could be a win-win at the end of the day.
But of course, the recipe for Coca-Cola would also be pretty important.
Sorry?
Never mind.
Okay.
Okay, that was the last question. We are out of time, unfortunately. But give a huge round of applause to Moritz and Alex, Alex and Moritz from Princeton University, getting rid of nuclear weapons.
Thank you.
Thank you. Thank you so much.
Thank you.